On a clear night, countless stars and galaxies light up the sky. Nowadays, telescopes supply fantastic pictures of them. It seems that if you had the right sort of spaceship, one day you might be able to fly to these stars. Oops! It seems not to be quite as easy as that to find a sensible route around the stars, because you keep crashing into objects which you can't see. In fact, to this day, 99.6% of the universe is still unknown, because it doesn't emit any light. Take, for example, black holes. In their vicinity, gravitation is extremely strong. In order to penetrate into hitherto unknown areas of the universe, Professor Carsten Dantzmann and his team want to prove the existence of gravitational waves. At the Max Planck Institute for Gravitational Physics in Hanover, the scientists are working on this form of astronomy. Cleanliness is very important, so that they can recognize what is invisible and prove its existence. When two black holes bump into each other in space, gigantic amounts of energy are released in the form of gravitational waves. They shake the universe.
Gravitational waves squeeze and stretch space and everything that is in it. Our planet Earth is squeezed and stretched too. First, like this, and then like this. That means it's obvious what we have to do to measure gravitational waves. We just need to measure how much the Earth is squeezed and stretched. Unfortunately, it's so little that this thing here is no help at all. To be exact, the distance between the Sun and Earth is squeezed and stretched by less than the diameter of a hydrogen atom. You have to look very carefully indeed. A ruler is no use. We need a laser interferometer.
And this is what the interferometer GO600 looks like. Underground pipes where all you can see at first is the cover. The pipes, or arms, of the interferometer run at right angles. They meet each other on the lower level. A laser beam is sent through both pipes and reflected at the end of the 600-meter-long stretch in each case. The principle behind it is quite simple.
This is our detector, and it's quite easy to understand how it works. Here you have our laser beams. They're absolutely identical and travel exactly as fast as each other. What we want to know is this arm shorter than that one? Or is that one shorter than this one? Or are they the same length? So we send the identical laser beams on their way along the arms. There they are reflected by mirrors and travel back again. And if the arms are the same length, what happens is they crash into each other. Now, I'll make one arm a bit shorter. The cars set off again. They follow their route. Moving forward, that one can already turn around and this one is still on its way. So what happens? They miss each other.
So when a gravitational wave comes, the length of one arm changes, and the cars miss each other. When there is no gravitational wave, they both stay the same length and the cars crash into each other. In fact, the scientists turn the laser beam signals into sounds, so that they can hear when there is a change in the length of the two sections. However, in order to measure as accurately as possible, there are other jobs that need to be done. For example, dirt on the path could slow down the cars, so the path has to be cleaned thoroughly. The scientists work in protective suits in a so-called clean room. They spend a lot of time keeping the various parts clean. For example, they keep cleaning the lenses in several stages. An earthquake. When the road starts shaking, this also affects the speed of the cars. So the road has to be protected against shocks as much as possible. It is cushioned. So each mirror in the GO600 is hung in such a way that the shocks in the ground are not passed on. The best road in the world is no use in a headwind. And even the resistance of the air itself is too much. So the scientists pump all the air out of the measuring area, and the laser beams run through a vacuum. In spite of all these measures, the scientists have still not managed to measure a gravitational wave.
Our detector works really well. We know that is the case, and we have been recording data for several years now. We would hear anything that happens in our cosmic neighborhood. The only problem is the universe is empty. Not much has happened there in the past few months. No star has exploded. There have not been any objects that have crashed into each other. So what can we do? We can either wait for a very long time, or we must become even more sensitive.
Becoming more sensitive means, let us assume that one arm is just a tiny bit shorter. Then the cars would still just touch each other. The scientists have therefore squashed the cars, or rather the laser beams, together. In this way, they have increased the accuracy almost tenfold. No more crashes. So now they are measuring the gravitational waves.
In fact, we don't want simply to detect the gravitational waves. That would be boring. We want to create a completely new kind of astronomy, gravitational wave astronomy. For thousands of years, people have been building better eyes, which we now call telescopes. They are the astronomers' eyes. But most of the universe is dark. We know today that 99.6% of it emits no light at all or other sorts of electromagnetic radiation. What we really need are better ears. And then the world would feel quite different. Just imagine that you are walking through a jungle and you're deaf. You can see the sun shining, the lianas, the trees. But if you are deaf, imagine how much would escape your notice. Now switch on your ears, and suddenly a completely new world opens up.
So the aim is to hear things happening in space. But from the Earth, that is very difficult to achieve. And so Carsten Dantzmann is already working on an even more ambitious project. In 2015, it is planned to set up several satellites to form a huge space interferometer, with arms that are 5 million kilometers long. It is planned that they should orbit behind the Earth and round the Sun in the shape of an equilateral triangle. With the space interferometer LISA, scientists hope to observe the most spectacular source of gravitational waves: the Big Bang. It is thought that the echo of this event can still be heard, because gravitational waves pass through matter virtually without losing their strength. The measurement of this background to the gravitational waves could give us information about the birth of our universe.